But in this lesson, we're mostly focused on writing down the chemical formula and learning about it. So let's take a look at the first one. Let's say that we have Mg, and then we have 3, and then we have PO, 4, parentheses, 2. Now what we want to do in this problem is we want to write down the number of atoms of each of the elements, how many atoms of each element we have here. So before we do anything, I want to remind you of something we said in the previous lessons. When you see some elements grouped in parentheses, we're actually going to have a dedicated lesson on this later. But basically, sometimes elements kind of come together and behave as a unit. We call those a polyatomic ion. Poly means many, atomic means atom, ion is an ion, which we're going to learn about later also, but it's a neutral, it's basically a charged entity. An ion either has a positive or a negative charge. So when you see parentheses here, this PO4 acts as a grouping here. So these, we have two of the, and the number 2 is on the outside of the parentheses, so we have 2 groupings of these entities called PO4. And we're going to learn the names of what they are because the polyatomic ions have names. We're going to learn those later. I don't want to do too many things in one lesson. So for this lesson, what we're trying to figure out is how many of each of these atoms we have. So Mg, if you're not sure, what is Mg on the periodic table? You go over here and you find Mg and you read that it's magnesium. That kind of makes sense. It seems to line up with magnesium. So how many magnesium atoms do we have? The number 3 is there, so we have 3 magnesium. 3 magnesium atoms. All right, how many phosphorus? If you're not sure about that, go to the periodic table and say, where is P? P is here, P is phosphorus. And so we have phosphorus. Now, there's an implied 1 right here, so you think there's only 1 of them. However, that is part of a grouping, which we call a polyatomic ion, and there's actually 2 of these entire entities. So what you do is you multiply the 1 here times the 2. 1 times 2 is 2, and so there's 2 phosphorus. 2 phosphorus atoms. And then we do the same thing with the oxygen. We have 4 oxygens bound up as part of this ion here, this polyatomic ion, but there's 2 of these entire things. So 2 times 4 is 8. There's 8 oxygen. Right? So 3, 2, and 8. All right, that was problem number 1. We're just counting atoms, just learning how to read these formulas here. Here we have Ba and then Cl2. All right, so how many atoms of each? So first of all, what is Ba? So if you're not sure, go back to the periodic table and you can see that Ba, where is Ba? Is barium down here. Ba is here and that's barium, pretty heavy element. And how many do we have? Well, we have an implied 1 here because there's no nothing else listed. So what we know then is we have 1 barium. Right? Now Cl is chlorine. If you're not sure about that, go read Cl, that's chlorine. And so how many chlorine atoms do we have? We have 2 of them. That's 2 chlorine atoms. And these guys are bound together. All right, let's take a look at the next problem. Let's say we have Fe, parentheses, NO2, close parentheses, and then another 2. Again, we have parentheses, so this is a polyatomic ion, which is kind of a thing, it's a grouping of atoms that like to act as a unit there. They're bound together. They're kind of as an object there. So over here on the front side, we have Fe. If you're not sure what Fe is, find it on the periodic table. And Fe is actually the symbol for iron. So something that you have everyday familiarity with. For iron, how many do we have? We have an implied 1 here. It's not written, but we know we have 1 iron atom. Not iron, sorry about that, iron atom. All right, how many nitrogens? N is for nitrogen. I think you probably remember that. There's 1 of them here. We multiply because we have 1 of them here, but there's 2 of these entire units. So 1 times 2 is 2 nitrogen. And how many oxygens? We have 2 here, but there's 2 entire groupings. 2 times 2 is 4, so 4 oxygens. Right, so 4 oxygens. So 1 and then 2, 1 iron, 2 nitrogens, 4 oxygens. All right, let's take a look at our last one. Our last one here is Ca, parentheses, OH, close parentheses, subscript 2. All right, so we take a look at Ca. You might guess that Ca is calcium, and you would be right because Ca is indeed calcium. So how many calciums do we have? There's an implied 1 here, so there's actually only 1 atom of calcium. right? What else? Inside here, this is a polyatomic ion that acts as a group, and we have two of these kind of groupings here. There's one oxygen here. 1 times 2 is 2, so 2 oxygens. And of course, I misspelled oxygen right here. I knew that looked weird, sorry. So, oxygen. Right, sorry about that. All right, and we have hydrogen right here. H is, of course, hydrogen. There's one of them. 1 times 2 is 2, so there's 2 hydrogens. Say hydrogen fast 10 times, and it's very difficult. Hydrogen, hydrogen, hydrogen. It's very difficult. So we have 1 calcium, 2 oxygen, 2 hydrogens. Okay. So that's what we, kind of a big skill that we want to do in the beginning is we want to write down a chemical formula and understand how many atoms are there. That's very important. The reason it's important is because later on when we do chemical reactions, we're going to have to understand the mass of each of the molecules or compounds that are there. And the only way you can find the mass of these things is by knowing how many atoms of everything is there. Because remember, the masses of each of these elements are written on the periodic table. So if we know the masses of the bariums and the chlorines, then we can, and we know how many of everything there are, then we can add everything up and find the total mass of the substance we're talking about, which is important for chemical reactions. So that's why we're counting atoms. Now, in this problem next, we're going to write down some elements on the board here, and we're going to ask ourselves, are they atomic or are they molecular? Because remember, in the last lesson, I told you that some of the elements on the periodic table don't really exist as separate atoms. I mean, you could rip them apart and make them into atoms, but in nature, they like to come together and bond together as diatomic molecules. Diatomic means 2 atoms. Molecule is a molecule, which is a joining, a bonding. So for instance, hydrogen is the one that comes to mind right away. Hydrogen, you don't really find it as a separate hydrogen atom. They always bond together and they make H2, hydrogen molecule. That's one of the diatomic molecules, and we listed them on the board before. So let's just take a look and write a few of these down and get some practice. What about neon? Is this exist as an atomic entity or a molecule? Well, neon is over here. It's one of the noble gases, and because it's a noble gas, we know it does. Anything in this column really doesn't bond with anything. Even helium doesn't bond with itself. It's not one of the diatomic molecules. But if you forget, just remember that the atoms here in the right-hand column, they're the most stable atoms on the table. We talked about that before. The noble gases don't bond with anything, including themselves. Or if they do, it's very, very rare in weird circumstances, okay? We're going to talk exactly why later that is the case. But because of that, we know then that neon does not exist as a molecule, it's atomic. So if you got a canister of neon, like you can get in a light bulb or something like that, then it's just individual neon atoms floating around in the gas phase. All right, what's the next one? Let's talk about fluorine. Is it atomic or is it molecular? Well, where is fluorine on the periodic table? It's right here. And if you remember back from the last lesson, fluorine is one of those elements that participates and it likes to be a diatomic molecule. It's one of the ones we listed. Again, if you forget, basically the ones in the noble gases don't bond to anything, so they're not diatomic, but the next door neighbors are in general diatomic molecules in this halogen column. And so since fluorine is there, fluorine is one of the diatomic molecules. You'll end up remembering it. So this is molecular. I mean, what you really see is F2. That's what you see. Just like H2 or O2 or whatever, you see F2. All right, so let's take a look at the next one. What about potassium? All right, where's potassium on the periodic table? It's right over here on the left. It's not listed as one of the diatomic molecules. It doesn't like to bond with itself, so this is just atomic. This is an atomic thing. So if you had pure potassium with nothing else, then it would exist as atoms. But I'll tell you that potassium is extremely reactive. In fact, the edges of the table are very reactive. Here, very reactive. Here, very reactive. The halogens, very reactive. Of course, the noble gases, they're the most unreactive, but basically right next to the noble gases, either to the left or wrapped around to the other side, extremely reactive. We're going to talk a lot more later, but it all boils down to the electrons that are there are able to participate in chemistry more readily than the other atoms on the periodic table. So because of that, they like to transfer electrons as they encounter other other atoms, and so they form bonds in chemical reactions. So you don't usually see pure potassium is what I'm trying to say. It'll pretty much bond with almost anything that it comes into contact with. For instance, oxygen in the air, it'll bond with oxygen, it'll bond with chlorine, it'll bond with almost anything on the right-hand side of the periodic table. And it's so reactive, it bonds with all kinds of things, so you don't really see pure potassium usually in nature. It's usually bonded to something. But in this case, that wasn't the question. The question was, is the pure substance atomic or molecular? It's atomic because it does not form a diatomic molecule. So when I say potassium is reactive, I mean reactive with other elements on the right-hand side of the table. It doesn't bond with itself. That's what I'm trying to say. All right, and here's our last one, part D. Part D is nitrogen. Is nitrogen atomic or molecular? Well, what are the diatomic molecules? Well, we have hydrogen that bonds with itself, that's diatomic. All the ones in this column, fluorine, chlorine, bromine, iodine, and also oxygen and nitrogen. These are not, of course, in this column, but they also form diatomic molecules. You see O2 gas, you also see N2 gas. So because of that, it's not typically atomic, it's molecular. In other words, you don't just see nitrogen atoms in a bottle, you see them bonded as nitrogen molecules, bonded in pairs, N2 like this. You'll end up memorizing which of the atoms on the table are diatomic molecules because you're going to see them in chemical reactions all the time. If I'm adding nitrogen to some chemical reaction, I'm not going to add it as just N because it doesn't exist as just N usually in nature. It's N2 or Cl2 or O2 or fluorine, F2, so things like this, H2 for hydrogen. You typically see them in reactions like this. All right, so we're almost done. So for the next problem, I'm going to write down some structural formulas on the board. Remember, structural formulas, they tell us the number of atoms present, but they also try to give us an idea of the structure of the molecule. It's not like totally accurate, but it's a quick and dirty way to see what the structure might look like. And what we're going to do is write down the molecular formula and then also the empirical formula. So this is a practice in understanding the difference between molecular and empirical formulas. So for the first one, let's just write it down. Here we go. We have a nitrogen bonded to a nitrogen, and then we have this nitrogen bonded to a hydrogen on each of its corners, so to speak. So you have these hydrogens bonded to this nitrogen, these hydrogens bonded to this nitrogen, and then these two nitrogens bonded together. By the way, each of these single lines represent a bond. A bond is an attraction between two atoms that is semi-permanent. You can break a bond by adding energy like heat or some other chemical reaction to break the bond, but left on its own, it's going to want to stay together. Just like H2O likes to stay together, those atoms are bonded. These lines represent the bonds. And because there's a single line here, these represent single bonds. Single bonds. But in chemistry, we're going to learn that we have single bonds, but then we also have double bonds, which are stronger. And then we actually have triple bonds, which are even stronger. But we're going to get to bonding later. I'm just trying to give you a little background as we go through this so you're not caught off guard. So this tells you a lot more than the regular formula because what would the molecular formula for this thing be? So let's write down the molecular formula. Right? The molecular formula just basically writes down the atoms that are actually present in the molecule. So we have 2 nitrogens, and we have 1, 2, 3, 4 hydrogens, so H4. So these are 2 different ways of representing the same molecule. Now, if I cover this up and I just tell you it's N2H4, that tells you the atoms that are present, but it doesn't tell you anything about the shape of the molecule. So it's good. I mean, we use that. We use it in chemical reactions. I mean, we don't want to be drawing pictures like hieroglyphics every time we write down a reaction. So we always write the molecular formula down in chemical reactions, but it just doesn't give that much information. Later on, we're going to find, way down the road in chemistry, that the actual shape of the molecule and how things are oriented in space actually governs a lot of what makes the molecule and gives it its characteristics. Is it a solid, liquid, or gas? A lot of time it has to do with the shape of the molecule. Is it very heavily reactive or is it not so heavily reactive? It can have to do with the shape of the molecule. If the molecule is very open and can allow things to come into the interior, and maybe break a bond or react, then it may be more reactive. But if the shape of the molecule is very closed off, where electrons really can't get in very easily or atoms can't get in very easily, then it may not be as reactive. So the shape of the molecule is actually critically important as we get later on in chemistry, especially into organic chemistry when we talk about organic compounds. But I'm just kind of giving you a preview mostly. So this is the molecular formula. Now, what is the empirical formula? Right? Empirical formula. Well, the empirical formula is the same exact thing as the molecular formula, except we take the subscripts and we reduce them to the smallest whole number ratio. So it still has N and it still has H, but if you think about it, just think about it as a fraction. I can divide both of these numbers by any whole number I wish to make it simpler. If I divide by 1, nothing changes, but if I divide by 2, and I have to divide both of them by 2, 2 divided by 2 is 1, so I'll leave that alone. 4 divided by 2 is 2. So I could write this as NH2. Let me move the N a little closer. So the empirical formula is NH2. Now, if you don't, in the beginning, we do this, but often students don't know why we're doing this. Why do we care about the empirical formula? Because the actual thing, the actual molecule is not NH2. It's actually NH4. So why do we even care about doing this? It's because if I give you a container and say, Jimmy, there's an unknown substance in here, but we know it has nitrogen and we know it has hydrogen, and go figure out what it is. Then what you're going to do is run experiments on it. You're going to run it through a mass spectrometer to figure out the masses of the different atoms there. And you're going to find the ratios of the atoms that are there. So you don't really know the actual structure of the molecule, but you can quickly figure out the ratio of the atoms. So what you're going to come up with in a lab is actually the empirical formula. The ratio of nitrogen to hydrogen is really 1 to 2. However, the molecule isn't just NH2, it's some multiple of that. But you start out by finding the empirical formula, and then you say, okay, it might be this, but it might be this multiplied by 2, which would be this. It might be this multiplied by 3, which would be N3H6. Because if you take the empirical formula and multiply it by a whole number, you get variations of it with the same ratio of atoms, but heavier and heavier molecules. So it's kind of like step 1 in analyzing a chemical compound is to figure out the empirical formula, and then from that, multiples of that might be what the molecule is. How do you figure out what the molecule is exactly and what is the correct molecular formula? Well, there's whole careers dedicated to that. You can do X-ray, you can do X-ray crystallography, you can do all kinds of things to figure out what the correct molecular formula is. But that's really the only reason why we're teaching this. The actual molecule really is N2H4, which is this one, and this is really what's floating around bumping into stuff. The empirical formula is the smallest whole number ratio from the molecular formula. All right, let's move on to the next one. I guess I'll do the next one under here. And I'll do the next one over here, actually. So let's call it part B here. So let me draw this. So we have nitrogen and nitrogen. Now we have what we call a double bond instead of a single bond. And then we have a hydrogen bonded right here and a hydrogen bonded right here. So this is a structural formula. What it tells me is I have a nitrogen bonded with a single bond to a hydrogen, another nitrogen bonded with a single bond to a separate hydrogen, but these two nitrogen atoms are bonded together not with a single bond, but with what we call a double bond, and we're going to learn about that later. For now, just know that a double bond is stronger than a single bond, and a triple bond is stronger than a double bond and a single bond. And we'll talk about why later. But basically, more electrons are being shared, and so there's more force holding these guys together. It would take more energy to rip this apart due to that double bond by adding energy or heat than it would if it were just a single bond. Okay, so that's the basic idea. But what we want to figure out here is what is the molecular formula. So I'm going to call this molecular formula. We're going to write down molecular formula first. Well, what is it? We have two nitrogens, N2, and we have two hydrogens, H2. So N2H2, that's a molecular formula. That's what's actually in the molecule. All right, now what would be the empirical formula? The empirical formula is when we take the molecular formula and we reduce it to the smallest whole number ratio. So I can simplify this like a fraction by dividing by 2. So 2 divided by 2 is 1, and H divided by 2 is also 1, so it becomes NH. So this is the correct ratio of nitrogen to hydrogen, But it's not actually what's in the molecule. It's a multiple of that ratio there. But you get the idea. If you were to analyze this, you might figure out that the ratio is 1 to 1, but the actual molecule is 2 to 2. And we learn how to do that when you get more advanced chemistry. All right, next, let's write the empirical and the molecular formula of the following. We have a nitrogen in the middle, we have a hydrogen bonded here, another hydrogen bonded here, and another hydrogen bonded right there. So what would be the molecular formula? The molecular formula is 1 nitrogen and 3 hydrogens, right? And the empirical formula, I take my molecular formula and I try to divide by whatever I can to make it simpler, but actually I can't divide by anything. If I divide by 2, then I'll have 1 divided by 2, that's going to give me a fraction. If I divide by 3, then I'm going to get another fraction. So you can't have fractional atoms, so you can't do anything. So basically it's just NH3. So the molecular formula and the empirical formula can be the same. In fact, water, H2O, the molecular formula, H2O, is the same as the empirical formula, which is also H2O, because you can't reduce it to any simpler whole number ratio. All right, there's some unspoken rules that I'm kind of showing you here. When I wrote these down, I wrote the nitrogens first and then the hydrogens second. I wrote the nitrogens first here and the hydrogens second. So generally, I mean, we're going to get into how to write them a little bit in a future lesson. But in general, you write the left-hand side of the periodic table first. When it's something on the left bonded to something on the right, you write what's on the left first and then what's on the right. And then when it's two elements on the right-hand side, then we're going to get into the details a little bit later of how to write them. So, for instance, carbon monoxide is CO, so we're writing the lighter element first. If it's H2O, we're writing the lighter element first. So generally, you're writing the lighter element first. If you have 2 things covalently bonded on the right side, or 2 or more, you generally write the lighter element first. But in this case, it's not quite right? Because I'm writing the heavier one first. So it's basically just things you pick up by observing. Because I can't really say there's like a definite rule that is always 100% followed. In chemistry, what you're going to find is we have a lot of guidelines, but we break them a lot. I mean, you can just see right here that when I said carbon dioxide, we write it as CO, or carbon monoxide, C, or CO2 or CO, we write it like that. So that would be the lighter element followed by the heavier element. But when hydrogen's involved, we don't write it with the hydrogen first. We always write it, well, in the case of water we do, H2O, we write it as the lighter element first. But in the case of NH3, we write the hydrogens at the end. So it's just, it's just different historical methodologies that were done in the past. We continue to follow them. What you're going to figure out is that as we go through these, the most common things that are reacting all the time, you're going to remember how to write them. And so there are some rules we're going to go through, but rules are meant to be broken, and we don't always follow the exact same rules all the time. You'll see that as we go. Now, as our last problem, what we want to do for our very last problem is I'm going to write 2 different structural formulas on the board, and we're going to talk about them. So the first one is the following. So I have a carbon bonded to carbon, carbon, and carbon. There's 4 of them. And then here's hydrogen. I'm going to go ahead and draw my little sticks first, my little bonds. All right, so this is hydrogen, hydrogen. Can you guess? Can you guess? Hydrogen. Lots of hydrogen. So this is what we call a hydrocarbon. And this is something we're going to study in great detail later. And this is something that happens all the time. You have a long chain of carbons, and then bonded to that chain is a bunch of hydrogens called a hydrocarbon, right? So this is one we're going to draw. Here I'm going to draw a similar one here. I'm going to have 3 carbons together, and then I'm going to have these guys down here like this, and then over here, and then I'm going to draw a longer one. It's going to be carbon right there, and then here. So I've got hydrogens, hydrogens, hydrogens. Here's another hydrogen, another hydrogen, another hydrogen, and now this carbon, I'm going to put 3 right here. Hydrogen, hydrogen, hydrogen. Now, look at this. Isn't this very rich? You can see that the richness in what's going on here, because the carbons can actually bond so many different ways. When we go to the periodic table, we're going to learn this later. We're going to have there's an entire class in organic chemistry that deals with carbon bonding. That's what life is made of, right? But you see, because carbon is right here, and it's 4 spots over from the noble gases, we're going to learn later that allows carbon to form 4 bonds. So you see this carbon is connected to 4 other things. 1, 2, 3, 4 single bonds. This one also connected to 4 other things. And it's mostly connected to hydrogens, but it can make a long chain of carbons here. And it can do the same thing, a long chain, but here we have an offshoot here. Now what I want to do, let's write down the molecular formula for both of them. Molecular formula, molecular formula. What is it? Well, how many carbons do I have? 1, 2, 3, 4. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. All right. Now what's the molecular formula here? It's carbon 1, 2, 3, 4. And hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now look at this. These 2 different molecules have exactly the same molecular formula. If I never drew any of this on the board, then if you would write this, you would see C4H10. You would write this, you would see C4H10, and you would think that they are exactly the same. And when you're just counting atoms, they are exactly the same. However, that is what makes the chemistry of carbon so important for life, and it's just such an incredible element that we need to live, because it can bond in ways that are like Legos and connect in different ways. Same number of atoms, but structurally they're totally different, because this one's a long linear chain with hydrogens connected, and this one has this offshoot up here. What we're going to find out later is that how things react, especially when it comes to carbon and carbon compounds, organic chemistry, is largely dependent on the shape of the molecule. I mean, it's dependent on what's in the molecule too, but it's also dependent on the shape. Because if you have, as I mentioned before, if you have a closed off molecule where it's difficult for anything to get inside to react, it's not going to be very reactive. Maybe not as combustible or something like this. Or if there's other things hanging off of that organic structure that are hidden or hard to get to, it's not going to react and it's not going to readily participate in anything. But if you have something unfolded and very linear like that, where things can get in we call it attacking the molecule to react with it, then of course it can be more reactive. So it is important what's in the molecule, but the actual geometry is critically important, especially with the chemistry of carbon, organic chemistry. So I'm kind of getting off to an aside, but I think it's fascinating that these 2 things have exactly the same molecular formula, and you would think they're the same, but they're actually totally different. And these same atoms can arrange themselves in different ways. Notice there's only 4 carbons and 10 hydrogens. What if I had 10 carbons and a bunch more hydrogens? Then the amount of combinations that you can make with 10 carbons is way higher. It could be in the thousands. You can have situations where you have thousands of different ways in which things can be connected with the same atoms. And so this is just something I wanted to mention to you. All right, so that's the molecular formula. What is the empirical formula? Empirical formula is when we take this and we try to reduce it. We can't really divide by 4. This would work, but this would divide by 4, give me a decimal. So instead I'm going to divide by 2. 4 divided by 2 is 2. H divided by 2 is 5. So C2H5. And the empirical formula here is exactly the same thing because it's the same molecular formula, C2H5. So in this case, the interesting thing is if I gave you a flask and said, hey, there's a organic compound in here, tell me what it is. Tell me what the molecular formula is. And this is an organic chemistry kind of deal. You know it's an organic compound. Then you go run your test on it, run it through a mass spectrometer, figure out what the ratio of the atoms are. You're going to come back and say the lowest ratio is 2 carbons for every 5 hydrogens. You're like, bingo, I've got it. But then you realize it's carbon. And so it could be almost anything because the molecular formula might actually be some multiple. Here is a multiple of 2, but it could be 3 times or 4 times or 5 times or whatever the ratio that you got. And then once you have the correct molecular formula, the structure can still be different even with the same atoms that are there. Because carbon can form these long chains. It can arrange itself in many different ways. And so you have to do a lot more analysis to figure out which of the 2 molecules you actually have. And in real life, you probably have a mixture of both of them. If you actually have a flask with molecules C4H10, then you probably have a bunch of different variations as far as the structure of the thing mixed in there. It may all be C4H10, but it may be different structures. So my last question here is, which of the 3 formulas gives you the most information about the difference between these 2 compounds? Which of these gives the most information is going to be the structural formula, right? Because it tells you the number of atoms there, and it tells you the shape of the molecule. I mean, it's not exactly a exact shape, but it tells you the main differences between the two. So if I just give you the empirical formula, that is not so helpful. If I just give you the molecular formula, it's still not so helpful. But if I give you one of these, you know everything that you can know about it. You know the number of atoms, you know roughly how they're connected. The only thing you can do beyond that is to make a three-dimensional drawing, because this is a flat drawing. In three-dimensional space, it may be twisted or something else, but the structural drawing still does give us a lot of information. So I could have blown through this pretty fast. I could have just written this down, say here's molecular, here's empirical, but I'm trying to tell you and give you previews of what's to come because I want to get you excited. I want you to go on beyond this and into organic chemistry. And a lot of people like organic chemistry because when they were kids, you play with Legos and you play with building toys. That's all organic is. It's connecting these atoms at the microscopic ways in many, many different ways. Even with the same atoms, you can have completely different shapes, which leads to completely different behaviors. All right, so at the end of the day, that is what we're learning about here. It's the idea of chemical formulas and the different models and ways in which to write them down and represent them. I'd like you to go through this again. When you feel like you understand, follow me on to the next lesson. We're going to start to talk about ions in chemistry. Learn anything at mathandscience.com.